All right, folks, welcome back to part two of the Win32 reverse engineering primer. So I don't have a whole ton of time because I had more technical difficulties recording. I have a little agenda I'm just going to go through real quick, but this is going to be good because you guys probably don't have a lot of time either, and so I'm going to keep this really concise, but give you a lot more tips on some things I didn't cover last time. So the first thing I want to talk about is IDA Pro real quick. You don't need IDA Pro in order to look up these imports and export functions, right? So in other words, in the last video, I was uh, I was clicking on the imports and the exports tab. Now you don't need IDA Pro to do that. You could use a program called Dependency Walker, which I linked to in the last video. I'll put the link in the description here too. You can even just use PE Studio like we did, and you could click imports or exports, and you will see the same thing essentially that IDA shows. Now it might be a little bit different because sometimes IDA and PE Studio are two different programs, and sometimes different programs find different things in different order and things like that. But you certainly do not need to use IDA Pro in order to view these imports and exports, because I know IDA Pro is an expensive program, and even if you get the free version, you're not going to be able to do 64-bit files like I am here, especially on like Windows 10 and stuff like that. So I wanted to put that out there. There are many other programs that can also look at imports and exports. There's pretty much any PE parsing program or portable executable parser can do that as well. And also there are other disassemblers like Radare 2 or Radair 2, whatever it's called, Hopper, Binary Ninja, and other disassemblers can do that. So the next thing I wanted to talk to you about real quick, which relates to stuff in the last video really, is these XAW type functions, which you will see. So let me go back to kernel 32 real quick, and I'm going to go back to the exports of kernel 32. So here we go. So I'm going to get rid of that so you could see without the yellow in the way. But see how we have load library A, load library XA, load library XW, load library W. It's like, what's going on here? Why are there so many load libraries? And then to make matters even worse, what happens is you go here and you do what I said, and you say, oh, well, Todd from Binary Adventure told me to go look up load library A, and it's not found anywhere, right? You see load library, but you don't see load library A. You look for load library W, you don't see a load library W either, you just see load library. But then you look for load library X, and you see load library X. But then you look for load library XA, and you don't see load library XA, you just see load library X. So it's very confusing, right? So what's going on here is there's only two different functions, and this is true for all of these. All these function types which have an X or an XA, XW, and just the regular version of it. What's going on here, which I'm going to show you in just a split second here, is that there's two different functions here at play. There's a load library X, and then there's a load library. That's it. And A and W are basically format specifiers. So let's just look at this real quick so you can see exactly what I'm talking about. So we're going to go to load library X, right? So load library X, this is the signature for the function. So it has three parameters. It has two ins and this reserved parameter right here. So it has H file, DW flags, and LP file name, right? So now what we're going to do is we're going to look at regular load library without the X, right? So we're going to look at regular load library. And you'll see that regular load library is a completely different function. It has a completely different function prototype, and it's not the same function. It may perform similar functionality, but it's not the same function. Now, A and W are not like this. So if you use load library A, you're telling the API that you are going to be using ASCII strings in it. If you use load library W, you're telling the API that you're going to be using wide strings or wide character strings in it. But the function itself, all the functionality is going to be exactly the same. So that's the reason why in the documentation they don't bother to have a separate listing for load library W, load library A, load library XW, load library XA. But when it's actually in the code, you will see those being in the code as different variations, like we saw here in IDA, where that actually is referenced. So that's the rundown on that. You're going to see this a lot. See, you can see it up here, K32 get WS changes X. Pretty much I can just search for XA here and you'll see what I'm talking about. Every single one of these, like see there's a create mutex, or there's a create mutex XA, create semaphore XA. There's a bunch of different things like that here. And the rundown for why there's an X at the end is X is basically like number 2. So for example, the first function they created was load library, like, or we're at it right now. And then later down the road, after they created load library, they were like, well, we want to let some of these application programmers have some more options other than just specifying a file name. So instead of changing the original load library, they just create load library X. So it's sort of like load library 2, or the sequel to load library. And you'll see a common theme where whenever you look at the X call, it usually has more options. So it's really the most commonly used one. So typically when you're looking through malware or reverse engineering programs, you're going to see the X one used more than the others. So virtual alloc X, for example, is probably going to be used more than virtual alloc because it allows the programmer to specify more things, and it might perform a little bit more functionality than regular virtual alloc. So you can see it takes H process, LP address, DW size, allocation type, and protect. And then regular old virtual alloc probably doesn't take all those parameters. It takes most of them, but there's going to be something different about, see, it says to allocate memory in the address space of another process, use the virtual alloc X function. So there's going to be something different where virtual alloc X can also specify which process, for example. That's the difference here. Whereas regular virtual alloc forces you to specify memory in the process that you're in, and that's it. So that's what that's all about. I'm going to be moving on to the next topic. The next thing I want to cover was books. So I mentioned them in the previous video, and I put them in the description a little bit, but I wanted to just give you a rundown real quick. So let's say you want to learn more information about some of this stuff, like what I mentioned in the last video was NTOS, kernel.exe, Wikipedia. So let's say you just want to learn more about how all this stuff works, because this is a lot to cover, and we're never going to cover all of it in this video or even on this channel, and I don't even know all of it, and I don't know if any one person knows all of it, because as you saw, the kernel has like 28,000 functions in it or something, and it's just a lot to know. Different teams of people worked on all of it. So if you want to learn more about how all this works, though, some of these other functions like the MM functions, memory management, MI, object manager, and all this kind of stuff for the RTL runtime library. The best books to read are a book called Windows Internals, and they have different versions of it for different years. So the newest version covers Windows 10, and it just came out at the beginning of this year, but it's only part 1. So they have 2 parts. They have part 1 and part 2. And because there's so much information to cover that it's actually 2 thick books every single time they update the book. And right now, they only have part 1 out for the Windows 10 stuff. So if you look at 7th edition and get that, you're only going to be able to get part 1, but it still covers a lot, and trust me, it'll keep you busy for probably a year at least, or at least until the second book comes out for Windows 10. So that's the first one I recommend. Now, if you want to learn more about just plain old Win32 user mode programming stuff, but native though, not C#, there's an old book called Programming Windows by Charles Petzold, 5th edition. It's a real thick book. It's old, but it's real good for teaching you how to create, like set up a window and do all that user 32 and GUI programming stuff. And then if you want to learn more about drivers and lower level stuff, then there's another book I recommend. It's called Programming the Windows Driver Model. And I'll link all this stuff in the description so you don't have to remember it. And then there's a final book where if you want to specifically learn more about the memory manager here, then there's a great book called What Makes It Page. And the guy's name is Martignetti. And he basically reverse engineered the entire Windows 7 memory manager and wrote a 500-something page book about it. And so if you want to learn how all that works, it's a great book to read. That should keep you busy for quite some time. There's a lot to learn there. So I wanted to cover those books. Again, they'll be in the description. And then the next thing I want to talk about is ORing things together. This is something that you will see often in Windows API programming. And if you're familiar with lower level C stuff, like if you've done embedded systems or other kernel or driver work or something, then this is not going to be a new concept for you at all. If all you've done is Python or something or C#, you may not have seen something like this. So this is a made-up function, by the way, but you're going to see this concept used all the time in Windows programming. So I wanted to show you this. So let's say we had a function called allocate memory, and we needed to specify a handle to the memory to the function. And then you saw code which said something like permission read or permission write or permission execute passed in as a single argument to the function, right? So that looks kind of weird, right? Because typically when you pass in an argument, a lot of times you're going to see just one single term, but here it looks like we combine like 3 terms, but it's all being passed before the comma into the argument, and it can be a little bit confusing as to what's going on here, especially with the OR. So even though it's called OR and it's using the OR operator, it's really combining all of this stuff. So what we're saying here is we want to allocate memory, and we want read, write, and execute permissions on the memory. So even though it says OR, in terms of what it means semantically, it's more of like an and. So we're telling the operating system, hey, give us some memory that's has read, write, and execute permissions. Okay. And so the question is, why do they do that, and how does that really work? And that's what I have down here. So what ends up happening is in the header file for this, which I can actually, if I can find it, I'll link it in the description as well, a header file for you to actually look at for the Windows APIs. So in the header file, they'll have something like this. It's not verbatim this, but they'll have something like this where they pound define a macro called permission read, and the last bit is set, and then they pound define another macro called permission write, and the second to last bit is set, and then they pound define another macro called permission execute, and the third to last bit is set. And what happens is that when you OR all of these together, it is a mathematical operation, and it turns all of those into one single number, and then that number gets passed into the function. So we're not actually passing 3 different terms into the function as far as the computer is concerned. What we're passing into the function is this number right here, because this number right here is the result of ORing all 3 of these numbers together. So and I'll show it to you live right here. I already did it, but I'll do it again here. So for simplicity's sake, we're gonna leave out all those zeros, but because it's the same thing. So if I do 1 or 10 equals 1 1. So if we only set these 2, the number down here would be 1 1, right? So in other words, it would be 0 1 1 like that. So then when we add the third one, when we do OR 100, because remember that's 100 right there. Now we have 1 1 1. And so this is nothing but a bunch of switches, basically. So this is a way to store some data in a very compact form in a single number. So we're only taking up 1 bit of space for each one of these options, which is really neat. That's one of my favorite things about low-level programming, is doing stuff like this. Is messing with these bits, because I mean, you're only taking up a bit of space to do this versus having to create up an object, throw it on the heap, and you're taking up 56 bytes and storing all this information like that. And that's one of the reasons why they do this, especially in embedded systems where you don't have a whole ton of memory and space to work with. And so what ends up happening is the function takes this number in, and then there is logic inside of the function internally that can figure out from this number that we wanted this information, or that we wanted these types of permissions. And that logic involves using a bitwise AND. So here we did an OR And then to undo this, basically you do an and in the function, and they can tell, they could do some processing on this number to see exactly what permissions we wanted, and then they could give us the permissions. So that's how that all works. Remember, what ends up happening here is that first it looks like this in the code, and then it ends up being replaced by this eventually, and then that's how the computer sees it, and it ends up turning into this, and then passing this as a argument into the function. So the next thing I wanted to cover was the NTOS kernel stuff in just a little bit more detail real quick. So let's just look at so in the last video we looked at NTDLL and kernel 32 DLL, and you don't really get to see a whole lot of functionality in those, right? So in other words, if you went to create file, you would just see like a stub that forwards to another function, and then another stub that forwards to another function, and you don't really get to see a whole lot about what's really going on. Well, if you go into NTOS kernel and you look up some of these, you're going to see something a little bit more interesting. So like, let's look at ZW create file. So if you remember in the last video, we talked about the SSDT, the System Service Dispatch Table, and that was a way for the user mode code in ntdll.dll to call a syscall or a sysenter instruction after it provided both the user mode stack and a given function lookup index or a function code, but I'm going to call it an index to not confuse you. So we looked at all that, right? And then once it passes that index into EAX and calls sysenter or syscall, then this is what basically happens on the kernel side of things, is that, believe it or not, even on the kernel side for ZW create file, there's another forwarder, and that ends up calling KI service internal. So if we jump there, KI service internal calls KI system service start, and this system service thing is what ends up handling that lookup. These are all part of that API, or that part of that functionality that handles the lookup. That's why it's called a service handler and all that stuff. So it cross-references the SSDT and figures out what functionality it needs to continue with. So for some of these, you'll see some more stubs like this. For other ones, you'll just see implementations. So for example, if we were to look at any of the KI functions in here, we're probably not going to see that, because KI means kernel internal only. So these are going to be like actual typical functions. Like KI, let's see if we can find something good here. KI and init system, right? So see, this is going to look like your typical IDA function, that you're looking through. It's not just going to be a stub, basically. And then you're going to be able to actually start reverse engineering and looking at the kernel and everything and all that. So to see really the lower level details of how things are working, it's helpful to go into ntos kernel.exe. That's the whole point behind this. And it's kind of neat to see how that whole system service table lookup thing happens. And so, which brings me to my next point of that whole lookup process involves several steps. So it's not as simple as I explained it, but it's not that much harder either. But there are several data structures and several functions that are involved. Like, for example, there's KI system service descriptor table, and then there's like KI system table and stuff like that. There's different data structures that are involved, but eventually you end up finding this list. So that's another thing I wanted to show you, is that even though last video I said that I couldn't figure out where the actual SSDT was, this time I actually have it for you. So I found it. I went to WinBag, which is the kernel debugger that you can use with Windows. I hooked it up to a virtual machine using VMware and virtual KD. I'll put the link in the description. And then if you type in this command right here with the live kernel debug session going on, see ntbang KI service table L1AD, then it will actually print out for you the entire SSDT. So these are all of the functions exposed to user mode through the sysenter instruction, basically. And this is so each one of these has a unique index number, which you probably can't see here right now, but each one has its own index number, and the number will correspond with one of these functions. And so now that we're looking at this, first of all, I wanted to show you that I went ahead and dumped this into a paste bin for you, and I'm putting that in the description. So if you just are curious and you want to see all these different functions and look them up yourself, you can go ahead and do that. And keep in mind, too, this is just for my specific version of Windows right now that I use, which I think this was Windows 7 that we're looking at here. So you might have more or less functions in your SSDT than me. That's fine, whatever. But I have about 406 or something like that we're looking at here. But this is kind of a cool concept because basically all of the user mode code, all of the application code that a programmer deals with eventually works through one of these functions, because everything from kernel 32 and user 32 and all these other DLL files ends up going to ntdll.dll, and then ntdll.dll ends up sending those index codes, and the kernel goes through this table and uses them. So, like, even if there's 20,000 functions exposed to the user mode programmers, they end up eventually filtering down to these like 400 or 500 that are here, and that does all of the lower level heavy lifting to bridge into the kernel so that the kernel can do its business, basically. So it's kind of a cool concept. Now, next thing I want to talk about, as you probably keep seeing here, is we have this NT exclamation point, NT write request data. So what's up with the NT exclamation point? What's that all about, right? Well, first of all, we don't pronounce it as NT exclamation point. We say NT bang NT create file, for example, right? That's how we say it. Or, for example, NT DLL bang NT create file. Or kernel 32 bang create file, right? So this is just a format for you to tell another programmer that I'm talking about NT create file inside of NTOS kernel, or I'm talking about NT create file inside of NTDLL, because there's an NT create file in both of those different libraries or executables. And so how are you going to know which NT create file I'm talking about unless I tell you, NT bang, NT create file, NTDLL bang, NT create file, or, for example, kernel 32 bang create file. So if you saw, for example, user 32 bang get window or something like that, I don't even know if that exists, but if you saw that, you would know, okay, we're talking about the function get window inside of user32.dll. So that's what that's all about, and it's just a nice shorthand way, and it happens to be that WinBag, this program, uses that, so you could actually talk to WinBag that way. And a lot of people who do lower level Windows stuff just use it to talk to each other in general, because it's convenient, and it tells you exactly which library you're talking about, as well as which function from the library that we want, rather than just having to say, let's look at NC create file from ntdll.dll. It's much quicker to just say ntdll bang nt create file. So that's what that's all about. And then, by the way, the reason why they have the NT bang, that's kind of confusing. So remember, NT bang NT create file is not NTDLL. It's NTOS kernel.exe create file. I don't think they wanted to do this. I don't think they wanted to do NTOS kernel bang because it's probably too long, so they just abbreviated it to NT bang. So that's why even when we're looking at these kernel functions, it says NT. So that said, NTDLL bang is actual NTDLL. I know it can be very confusing with all the NT stuff, but that's just what Microsoft decided to do. They were super obsessed with this whole NT thing. So, so that's how that works. In fact, it's very confusing because a lot of the NT functions are both in NTOS kernel.exe and they're in NTDLL. And generally, when they're in NTDLL, they're just forwarders to the NT, to one of these SSDT internal kernel functions here. Okay, so so another thing I wanted to say real quick is this. So this whole thing, this SSDT, System Service Dispatch Table, is just a lookup table. It's not. It sounds super complicated and all this stuff, but it's not at all. It's basically just an array of function pointers to each one of these functions. That's what we mean by a lookup table, and they just have a really cute name for it. System Service Dispatch Table. Sometimes it's called System Service Descriptor Table. But it's usually abbreviated SSDT, and I'm going to post some links in the description to some more information on breaking that down and looking at some of these other structures that are involved and at play with this whole lookup process. And I think that's it. Yeah, I covered everything I wanted to cover. Hopefully it worked this time. Thank you guys for watching, and gals. I hope you have a happy holidays, Merry Christmas, a great New Year, and don't forget to subscribe if you like the content here, and feel free to ask me any questions in the comments. Also, you can go to malwareanalysisforums.com and ask me any questions on there, or you can go on my Twitter, MOVEAX41H. But here, go to malwareanalysisforums.com. Feel free to post any questions that you have, and I check this pretty frequently because I created the website and everything for people to learn. But even if it's not malware specific, you can still ask the question as long as it's reverse engineering related, and I'd be happy to help out there. And then one thing I wanted to say real quick before I left, which I probably should have said at the beginning, is feel free to watch my videos in 2x speed. I do that a lot too because we all are short on time. Reverse engineering takes forever, and there's no need to sit here and listen to me ramble if I'm going too slow for you. So just go to YouTube and go to hit the little gear at the bottom right of the screen, and then speed up the video to 1.5 or 2x. I've tried listening to myself in a fast speed, and I can understand myself. Not everybody is easily understandable if they already talk really, really fast. But I was able to understand myself, so just give it a shot. See if you can, if you understand English fluently, then you might be able to listen to me in 2x. That way you can get the video done in half the time. So again, thanks for watching, and I hope you guys have a great day. Bye.